Hello. Just waiting to see if more people show up. I'll wait until 10 after before I start, because, you're the only one. All right. So for tonight, do a little bit of review, and then we have a bunch of different topics on this slideshow, so we'll just kind of see how far we can make it. This is the last class. So hopefully we can get through most of this. These are all to do with just straight lines, so it's not too bad. The tougher part is probably just going to be the review stuff. Okay. So last time we did some triangles. Triangles, of course, are three-sided shapes, and there's a bunch of different classifications of them. Equilateral triangle has all three sides being equal. By extension, all the angles are equal. Isosceles triangle is a fancy word that's basically just saying that there's two equal sides. So instead of the equilateral where they're all equal, in this case you have just two of them equal, so you can kind of, like it says there, kind of a mountain with equal slopes on both sides. You can kind of visualize that. Then we have scaling. Those are kind of the most, basic thoughts of a triangle. No equal sides or angles, so everything's at least a little bit different. And right triangles, those are the ones we use the most in math because they're most useful. They have 190-degree angle, which is the right angle, and the side opposite that right angle is called the hypotenuse. That's always going to be the longest side of the triangle. Okay. And then in working with triangles, we, just like other shapes, have to play with perimeter and area. So perimeter is pretty easy, you just add up all the sides. Area has its own formula though. Area of a triangle is 1/2 the base times the height. The tricky bit on that is that most of them you don't know the exact height. So usually what we end up having to do is kind of draw a right triangle coming down from the highest point to kind of give us a height. And then in order to figure out the missing side that we really need, we have to use something called the Pythagorean theorem. And the Pythagorean theorem actually relates all three of the sides of a right triangle together. So if you square both legs and add them together, it equals the square of the hypotenuse. Or more fancy here, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the other two sides. So you square both legs, add them together, equals the hypotenuse squared. Pretty much it conceptually. So we do have some examples to work. First one says a right triangle has a hypotenuse of length 13 units and one leg measuring 5 units. What is the length of the other leg? So something like that, we'd use the Pythagorean theorem. I'll go ahead and draw that out real quick. Okay, so we have triangle. We know one of the legs is 5. Now you could have drawn that 5 up here. It's honestly, math-wise, it's not going to work out to make a difference. But either way, one of the legs is 5, and then the hypotenuse has a length of 13. So we need to know what this side is. So if I consider this leg A, then this would be leg B. Doesn't really matter what I call it, but we gotta call it a variable. But I'm calling it B because the formula is a squared plus b squared is equal to c squared. And we know what two of those are. If this is leg A, this leaves this to be our C. Then the only thing we're missing is the b. Since that's 2 out of 3 of these variables, that means we could solve for it. So I'm going to substitute in 5 for the a. We don't know what b is. And then c is 13. So we have 5 squared plus b squared is equal to 13 squared. So 5 squared is 25 plus b squared is equal to 13 squared is 169. I'm going to subtract off the 25. Negative b squared is 144. And in order to get the b alone, to cancel out the square, we have to take the square root of both sides. The square root of b squared is just a b. The square root of 144, that's a perfect square of 12. Okay. I don't believe this had any units on it. Yeah, it just had the word units. So that means that our answer will be 12 units. If this was 5 units, this was 13 units, then we'd call this 12 units. Okay. All right. Another. So the second one says a square has a diagonal of length 10 units. What is the length of each side of the square? Hey, Ruben, good to see you.
Hello,
Hey, hey.
how are you today?
Been better, been worse. How are you?
Fine, thank you.
Good, 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 good. Looking at number 2, it says a square is a diagonal of length 10 units. What is the length of each side of the square? So we have this figure here, where our diagonal is 10 units. That says units, I promise. And we need to figure out what the lengths of the sides are. I don't know what variable to call it, so how about S for side? We don't know what that is. All we know is this guy. Well, that's enough, actually, because if I was using the Pythagorean theorem, yes, we normally need to have 2 pieces of information to be able to solve this. And we only have 1. But what we also have is the fact that all the sides are the same. So if I'm using, say, this triangle right here, kind of boxed in there, then I know that both of the legs are equal. They're both S, right? So I'll have S squared plus S squared is equal to our hypotenuse squared, which is 10. 10 squared. And see, these guys are like terms. Since it's the same variable, we can get away with working this problem. So if I had s squared plus another s squared, that means I have two of them. So I have two s squareds. And 10 squared is 100. Now I'm going to try to get the s alone. So the first thing I gotta get rid of is that 2. Since it's multiplied onto the s squared, we're going to divide it off. Divide off the 2 on both sides. We get s squared is equal to 50. And since we have an s squared, we're trying to get the s. We need to square root both sides. Square root of s squared is just an s. Square root of 50, well, it's probably 7 and change. I'm going to go ahead and get a decimal. So I get about 7.071. So this is the length of each individual side. So since this was in units, this one we're also just going to say it's that many units. Okay. Real quick. Right, so we have a couple more. Number 3 says an equilateral triangle has a perimeter of 36 units. And it wants the side length and the area. Remember, equilateral triangles are the ones where the sides are equal every time. So this is some amount, this is that same amount, and this is that same amount. Okay. So if we need the side length, well, it would make sense that if all of these are equal, I could just take my perimeter. Let's call this S, just so we have something to say it is. The side is 36 divided by 3, right? So I get 12 units. Okay, so we have that piece of information already. Now we just need the area. Well, the area of a triangle is given by 1/2 the base times the height. Well, we have a base. That's the units here, but we don't have a height. We need that height. So what we're going to do is make a right triangle out of this. So if I know every side of this thing is 12 units, then that means that this here, which is the same as the hypotenuse over here, is going to be 12 units. And then if this is 12 and I'm cutting it perfectly in half, this down here is going to be 6 units. But we still need to know what the height is. So in order to find that, we're going to have to use the Pythagorean theorem again. So we just have fun with it. A squared plus b squared is c squared. Now, we could say these guys are our legs and this one's the hypotenuse. Which leg's which doesn't much matter. Let's say I decided this was A, so I had to have 6 squared plus the other leg, which is an h squared is equal to, and then our hypotenuse squared, so 12 squared. Then we're going to clean this up and solve for h. 6 squared is 36. 12 squared is 144. And get the h squared alone. So subtract that 36. If I do this minus that, I end up with 108. Now I need to figure out what the height is. H squared, to cancel that square. We're going to square root both sides. I'll get the h alone over here. Over here, I don't know what that is, so I'm going to throw it to the calculator. I get something like 10.3923. So that's our height. Okay, so don't think we're done yet. Remember, we're not looking specifically for the height. We're looking for the height because we needed the area. So the area formula needed that h. So we can go back to our area formula. And going back to our original figure, it's 1/2 the base is this guy, which was 12, right? Times the height, which our height we just found is 10.3923. Half of 12 is 6. And I'm just going to multiply that in there. End up with the area is equal to 62.3538. Then we need units on this guy. Well, we weren't in feet or meters or whatever, we were in units. So if I have units times units, I'm going to end up with square units. Okay. Any questions on that one? All right, let's do one more. It says a triangle has two equal sides measuring 12 inches. And the perimeter is 48 inches. Calculate the length of the base. And find the area. Okay. So since two of the sides are equal, I just said side equals 12 and side equals 12. Make a figure on this. So we know we have two equal sides. I'm going to treat those as these ones over here. So I'm going to just call this 12 and this 12. Do we have any units or just the word units? Inches. Okay. Everything's in inches. So each of these is in inches. Okay. Now, we need to know what the base is, but we don't know what it is because, well, we're just given the perimeter. So if I decide to slap a B on there for base, then I know that our perimeter is the 12, and the base, right? So things I know the perimeter is 48. And I don't know what the B is, but now that it's the only variable, I can solve for it. So I'm going to combine like terms. And I'm going to solve for that B. 48 minus 24 is another 24. Equals B. So we have 24, and our unit is inches. That'll be the length of our base. Now we need the area. And just like the previous problem, we don't have the height. Remember, the area formula is 1/2 the base times the height. We got the base, we just don't know the height. So I'm going to bust this out as a right triangle. And if this base is twice, well, it's twice half of it. I guess that's a weird statement to make. But if I chop this base in half, I would still have a 12 inches down here. We got our own little equilateral triangle happening here. Well, let's see what happens. Okay. You have to do the this is gonna break. Yep, this is gonna break. This is a trick question. So let's follow through until we run into why it's a trick question and then discuss that a bit. So each of these 12 squared is 144. But if I solved for h, h is 0. Well, that's a problem, because if the height was 0, well, we wouldn't have a triangle, right? And see, that's the only way that this problem would work, is if there is no height. We essentially have a flat line that we've counted the perimeter around. See, because if this is 12 inches and this is 12 inches, and then we're supposed to have like a full other half of this where it kind of encloses some space, there's no way to have 12 inches here and 12 inches here, but some height in here that lets us put another right triangle on the other side of it. See, if you look at our original figure here, we know this is 12 and this is 12, and we found that this is 24. Well, if this distance is 12 and this distance is 12, then that distance is 24. You can't take 24 here and then bow this out and say that's also 24. It breaks. Now, I suppose it could be argued that even though this doesn't end up counting as a triangle, we could still have an area. It's just the area is 1/2 the base times the height, and the height is 0. So 0 times any of this stuff is just going to give us a 0. There is no area because this ends up working out to being a straight line. That's kind of an interesting one.
It's a weird one.
Yeah. But that's the way the numbers fell. If it had worked out a little differently, if this had been anything other than 48 for the perimeter, maybe like 36, then this would have been shorter. Then there would have been able to be a height because the base wouldn't equal out to the two other sides. But such is life. Got a weird one, so there's no height. I suppose a nice way of saying this would be that there is no triangle to speak of for this problem. Or maybe no solution. Either way, it'll work.
No solution sounds better.
Yeah, yeah. All right. Look at a couple of examples for circles. Review's taken a little bit longer than I was hoping. Just fine. Oh, I think I actually meant on, there we go. Deleting that slide. So circles. Circles are perfectly round shapes where all points on the edge are equidistant from the center. So basically, you got a point, and then you just kind of have a distance around that point the whole way, and then you end up with a circle. So the distance between the center and that point is called the radius. And the diameter is actually a measure of the length, the longest length through a circle, which would have to go through the center. And because of that, the diameter is just twice the radius. So if you have the diameter and you need the radius, you could chop it in half. If you have the radius and you need the diameter, you can just double it. And then we have the mathematical constant pi. That represents the ratio of a circle's circumference to its diameter. So any circle on the planet, if you divide its circumference by its diameter, you will always get pi. So that's actually one thing where I had some students do long division with the circumference and diameter of a circle to show them that it actually did end up computing pi. And if we were accurate, particularly accurate about the diameter in that particular case, we would have been able to take as many digits as we wanted to. But yeah, it's anytime you see pi hanging out in a formula or something, it is a number. It is a number that we always have an answer for. It's not a variable, but since it's used in a symbolic form, since we use its symbol, we can kind of do the math with the pi symbol similar to how we do it with a variable. So we kind of leave pi to be pi until we actually need a decimal number. Like I said last time, chances are you have a pi button on your calculator. Some people are perfectly happy with rounding that off to 3.14. I am not. I don't feel like that gives us enough accuracy. So I would either use a couple more digits than that, or just use the pi button on your calculator because it has more digits than you're ever going to need. At least in my case, computes it out to 11 decimal points, it looks like. No, 12 decimal points, which is far more than you'll ever need. Now, when it comes to circles, we have a couple of things that we can find. We can find the circumference and we can find the area. The circumference is essentially the measure of its perimeter. It's the measurement around the outside of the circle. And the area is, of course, the measure of the enclosed area in a circle. Both of these have formulas that deal with pi. So the circumference is 2 pi times the radius. So you can abbreviate that as C equals 2 pi r if you would like. And then the area is pi times the square of the radius. So you can call that area, or A equals pi r squared. Either way, it works out nicely.
El misil secreto que puede este pastor.
We got a couple of examples. The first one says the circumference of a circular track is 100 meters. And we want to know what the radius is. And this one's a particular simple, actually all the examples for circles are simple. Because all we have to do, well, we have our formula is 2 pi r, and we know the c, we just don't know the r. So we just solve for it. So we're going to say our circumference is 100. And then to solve for the radius, we're going to divide by both the 2 and the pi. Comes to dividing by 2 pi. Actually, let me use the other calculator for a visual. When it comes to dividing by that, you want to make sure that you put that 2 pi in parentheses. Because we're dividing by that whole thing. And if it helps you, you can just go ahead and put parentheses around it in the problem. That's no issue. So we get about 15.915. Now, if I hadn't done that, thank you, calculator, appreciate it. If I hadn't done that, I would have ended up with 157, which is almost 10 times this number. And the reason for that is because between these two symbols, the 2 and the pi, well, what's happening? They're being multiplied. Well, what ends up happening with the way the calculator is interpreting it is it's seeing that multiplication happening. So what the calculator is doing is it's just doing 100 divided by 2. And then it's taking that and multiplying it by pi, essentially taking that pi and putting it up here. So the way the calculator interprets that can throw you off. So what I usually recommend is if you're going to be punching in multiple pieces into a calculator, anytime you have like multiple pieces, put a parentheses around it. Because if I put a parentheses on this, what it's going to see is it's going to say, hey, this is 100 divided by that whole thing. And that's why we have that difference in our numbers here. So if you don't put that parentheses, it's going to apply it incorrectly.
So we have to use the parentheses.
I'm sorry, what was that? You cut out a little bit.
Yes, we have to use the parentheses.
Yes. And like I said, I would recommend using that as often as need be. Anytime you have something more than just, hey, I'm dividing by a number. If I'm dividing by 2 numbers in this case, put a parentheses around it. If it's more complicated than a number, put a parentheses around it. You're usually going to be safe that way. God knows I have been very parentheses happy with my problems. And it's never steered me wrong.
So in this case, the answer is 15.915.
Yep, and I almost forgot my own big thing. If I have a unit on the end, I need to make sure that that's part of my answer. So it's 15.915 meters.
Interesting.
Yeah. Okay. Number 2 says a circle has an area of 78.5 square inches and calculate its diameter. Okay. So if this is my area, we have to have our formula for the area of a circle. Just pi r squared. And we know the A part is going to be this number, so I'm going to go ahead and set it equal to that. We're trying to get the r alone. So the thing in our way is that pi. So we divide off pi. So 78.5 divided by pi. We get our radius squared is equal to about 24.987. Then to solve for the radius, I'm going to square root both sides. So the radius is going to be given as, that's interesting, 4.9987. Makes sense. This is really close to 25, so the square root of that is going to be really close to 5. Okay. So if that's our radius, what's our diameter? Well, the diameter is always twice the radius. So if I double that, then that'll give me the diameter, which is going to be 9.9975. That's, again, going back to our units. Our units were originally in inches squared. This is a distance, so this is now in inches. Now, chances are, based on how close that was, chances are that this 78.5 was actually calculated out with a rounded off pi. It was actually counted up, like worked out that way, because if I had rounded to that many decimal places, I have 3 total numbers here. If I had rounded the 3 total numbers here, or here, or here, this would have been a 25, a 5, and a 10. So chances are this problem was originally made for a shorter value of pi, but since we used our actual pi button, then our numbers are ending up a little bit more accurate than you would expect normally.
In this case, you divided 24.987 for pi.
What I did, well, we divided the 78.5 divided by pi. That gave us the 24 and change, but then the 24 and change was equal to r squared. So because it was equal to r squared, we needed to square root both sides. And that's what I did there. We square rooted this 24.987 and we got this guy for the radius.
Okay.
Yeah.
Because I'm trying to learn how to use a calculator using this, like the pi and all the symbols like that. Because if I don't put the right symbol, it's totally give me different answer.
And you're not wrong, it'll do that.
Yeah. So, okay, thank you.
One more circle example left. Gonna fit that over here. So it says that the diameter of a circular swimming pool is 20 feet, and we want the circumference. So we have the diameter, we need the circumference. Well, our circumference formula is 2 pi r. We don't have an r, but we have d. And remember, diameter is twice the radius. So if I have D is 20 feet, then our radius is going to be half of that, 10 feet. Now we can take that radius and plug it in for our formula. C equals 2 pi times R, which is 10. This is something we can actually throw at a calculator. So 2 times 10 is 20. So 20 times pi. We end up with something around 62.832. And that'll be in feet. And that's what we have to do for that one. Yeah. Not too bad. Now, the last stuff I have for review is kind of the trickiest stuff we've looked at, right? And to be fair, I did skip ahead a couple of chunks of information to cover this. Because honestly, I just felt like if anybody was leaning towards testing, this would probably come up a couple of times. So I figured that this would be worthy to include at the end of the class. And that was the quadratic formula. So if you remember, quadratic functions, they're just a formula, any type of function that has the variable x raised to a power of 2 as the highest power. So you generally have something where it's something x squared plus something x plus something else. And notice how the formula there uses a x squared plus b x plus c. The a, b, and c are useful for us because with that a, b, and c, those are being the coefficients. We actually have a formula to find the solution to this problem right away, just based on those 3 numbers. Now, the downside is memorizing that thing. The upside is generally you do it so often that it's really easy to memorize. And that's the big ugly formula at the bottom. X equals negative b plus or minus the square root of b squared minus 4ac. That's all divided by 2a. Okay, so instead of having some long-winded example, I have a couple of problems for it. So the first one, we have 2x squared plus 5x minus 3. And remember, we're going to need to know all of our coefficients, at least till you understand what's happening. I recommend just writing out a equals whatever's on the x squared, b equals whatever's on the x, and c is equal to whatever the constant term here is. Now we need our formula. Formula is going to be given by negative b plus or minus square root b squared minus 4ac all over 2a. So We're gonna take these three pieces of information, and we're gonna plug them in here. So negative b is 5, so negative 5 plus or minus square root b squared, so 5 squared, minus 4 times a, which is 2, times c, which is negative 3, all over 2 times a, which is 2. And see, all I've done is I've replaced our variables with those numbers, but in a set of parentheses. That way I could see where things are getting multiplied and how. Just kind of works out a little nicer that way. Now, to be fair, this is, like I said last time, this is where you could cut a few corners. If I'm writing b squared right here and I see a 5, I could just write 25. If I see 2a here and I know a is 2, I could just write a 4. You can just, you know, cut down little tiny steps like that just to make your life easier. All we're going to do for the next step is just trying to clean this up as far as we can go. So this will be a 25. Now, this is minus, and it's multiplied by a negative. There's going to be a plus here. 4 times 2 is 8, times 3 is 24. That is all divided by 2 times 2, which is a 4. Now, the only thing I can do to clean this up right now is just add these two numbers together. So I'm going to have a quick little step for that. And in the case of this problem, we have the square root of 49. That's a perfect square. So what we could do write it that way. Now, a lot of times you end up with a square root staying here, and that's usually where you would just box this up and say, okay, those are my two answers, is the plus and the minus. But whenever that breaks down to a solid number, I like to split it up and find the two separate answers individually, okay? So in one case, we're going to have negative 5 plus 7 all over 4. And in the other case, we're going to have negative 5 minus 7 all over 4. So we've just split this up based on the plus or minus symbol. So one of them has the plus, one of them has the minus. And now we clean them up. Negative 5 plus 7 is a 2 over 4, which reduces to 1/2. Then down here, we have negative 5 minus 7. That's a negative 12 over 4. Ah, that goes in nicely. 4 goes into 12 3 times, so we have a negative 3. And those would be our two answers. Ooh. Isn't that fun? I know, it's not, but still.
Looks fun, but it's not fun.
Yeah. Hey,
What's happening?
oh, you know, I'm alive.
Everything on Zoom?
At the moment, yeah.
Or talk to you later.
Later. Yeah, so the next one, we have 4x squared minus 9. So one thing to notice is that we have our A, we have our C, but we don't have a B. There's nothing there. We don't have that term with just an X on it. So when that happens, you're gonna say it's 0. We don't have it, it's not there. Now from here, based on those 3 numbers, we're going to do the exact same thing. So I'm gonna write out the formula again. Negative b plus or minus square root b squared minus 4ac all over 2a. And let's see what we get. So our b is 0, so I don't have anything here. Square root of, well, b squared, that's still a 0. Minus 4 times a, which is 4, times c, which is -9. All over 2 times a, well, a is 4. This will be an 8. And now we can clean it up. So we have nothing here, so I'm just going to lead with that plus or minus. Square root, well, we have nothing minus, and then something multiplied by a negative. So these 2 negatives are going to cancel each other out. This is going to end up being a positive number. So we end up with 4 times 4, which is 16, times 9, which is 144. That's still over 8. Well, square root of 144, that's 12, right? So we have plus or minus 12 over 8. And then we can reduce that. 4 goes into each of these. 4 goes into that top one 3 times and into the bottom one 2 times. Now, this is where I would box my answer. I will say this is 2 separate answers because of that plus or minus. We have both a 3/2 and a -3/2. But since it's the same number, I went ahead and just rolled with it with the plus minus because that's just as accurate. We have both numbers represented by one symbol, basically. So it works out quite nicely there. We have just one more. So we have 6x squared plus 11x plus 3. In this case, we do have an A, a B, and a C. I don't really need to write the formula again, but I'm going to just for repetition's sake. Negative b plus or minus square root b squared minus 4ac all over 2a. Now I'm going to take all 3 of these numbers and plug them in here. X is equal to negative b, well, b is 11, so negative 11 plus or minus the square root of b squared. So that would be 11 squared. I'm going to go ahead and multiply that out now. So it's 121 minus 4 times a times c, 6 and 3. That whole thing is over 2a. A is 6, so this will be a 12. Now all we got to do is just start cleaning it up. So here we have 4 times 6, which is 24 times 3, so that should be a 72. So if I do that subtraction, I get the square root of 49, which again is 7. So I get negative 11 plus or minus 7 over 12. And this is where I would split it off as two separate answers, because I do have something in front of that plus minus, unlike what happened over here. This is going to give us two completely separate looking answers. So I'm going to have x is equal to negative 11 plus 7 over 12, and x is equal to negative 11 minus 7 over 12. So right here, I get a negative 4 over 12. And 4 goes into each of those, so it reduces to negative 1/3. That's one of our answers. Then down here, we have negative 11 minus 7, so that's negative 18. Well, that also reduces, right? 6 goes into each of those. So we get negative 3 over 2. There we are. So the main thing with these types of problems is knowing the formula. Once you know the formula, you can write out what it is you have and plug it in. At that point, other than having to clean this up, you're basically done. It's just all cleanup, right? All simplified. And that's fine. Just take it as many steps as you need to, and you're going to end up with the right answer. I think we're content with leaving that behind. Our next subject is reading and interpreting tables. So this is pretty simple, right? For the most part, we've all kind of seen tables already. The next one is circle graphs. We've all seen circle graphs already. It's all just about being able to extrapolate information from what it is we're working with. So obviously, I'm not going to go to the notebook on this one because, well, I'm not going to draw out that table. That would take too long. We do have a fair amount of questions on it. I'll just kind of look at it together. So number 1 says how many countries are in this table. I'll go ahead and get the spotlight out here. Okay. So how many countries are in this table? Well, there's our country header. So we're just going to look 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 countries in the table. Which countries have over 1 billion people? Well, you'd look at the population, you'd look for 1 billion, just be these two. So that would be China and India. How many people live in the USA? So the USA, population 314 million and change. What is the most populous country in each continent? Well, then you would, since this is sorted by population, you're able to just look at the continent table and kind of work your way down. The first time you see Asia is in China. So that's the most populous Asian country. Then in North America, it'd be the US. Skipping the Asias because we already covered that one. Brazil is in South America with 193.9 million. Skipping Asia, we have Africa, which is Nigeria. That's 166 million. And then Russia is kind of Europe, kind of Asia, right? Nothing in Europe is going to win any population, badges. It's not the biggest. So in this case, it would be 143 million. Yeah. Which continent contains the most populous countries? That should be pretty evident if, we're at 2.5 billion between China and India alone. You could also look at the world population percentage, like 19% of the world and 17% of the world, just those two countries alone. Yeah, that kind of dwarfs any of these, right? So it definitely would be Asia for the answer here. And then of the 10 most populous countries, how many are in Asia? Well, this is 10 countries. So 1, 2, 3, 4, 5, 6, and 7. Yeah, we'll count Russia. So, I mean, pretty much everything except for Nigeria, Brazil, and US, right? And that's really like, as long as you can look at a table and be able to interpret the data, that's all you really got to worry about, right? That's not bad. Now, the only other thing I have for you on charts and tables would be circle graphs. So circle graphs is actually one of the most used kinds of graphs, because you kind of have like, they're also called pie charts. But it's just a big circle and everything in the circle adds up to 100%. So each sector, all of the sectors combined should add up to 100%. This is particularly useful because a lot of times you can use a circle graph and kind of take information at a glance, as long as it's made accurately. If it's made inaccurately, not to scale, then you have a problem. So take this example. It says favorite pizza toppings. You have pepperoni, cheese, sausage, and supreme. And you can very clearly see, okay, there's different colored levels for everything, and it gives you a general idea of the breakdown. So question-wise, says a survey of 320 people was conducted. How many people preferred supreme pizza? So you would look at the supreme, which is the red color, say, okay, it's 10%. Well, if we want how many people that is, we need 10% of 320. So you would do 0.10 multiplied by 320, and you would get a total of 32 for this answer, right? Number 2, how many more preferred pepperoni pizza over cheese pizza? Well, pepperoni is 50% and cheese pizza is 25%. So to figure out how many more preferred pepperoni, you would find the subtraction between those, which would be 25%, right? And we'd have to find 25% of the 320 people. So 320 times 0.25. So looks like it's only 80. So there's 80 more people that preferred pepperoni over cheese.
Did you say 320?
Yeah, because we're comparing the percentages.
Mm-hmm.
So it wants to know how many more preferred pepperoni over cheese. So the first 25 over here doesn't count as much because, well, that's how many. That would be where they'd be equal. But since we're looking for how many more, we find the subtraction between the two percentages, then you have the 25% here, and you're going to multiply that by the 320. So 25% times 320, you would change it to a decimal, so you'd have 0.25 times 320, and that's where you get the 80.
Okay.
And then number 3 says what percentage of people did not prefer pepperoni or sausage? Okay, so that would leave cheese and supreme. So cheese was 25%, supreme was 10%. So adding these two together, you have a 35%. So you could do 0.35 times the 320. And get 112. The other option would be, that's kind of the addition of the answers to number 1 and 2, right? Number 1 was looking at just the supreme. And number 2, let us figure out what 25% of this thing was. So 10%, 25%, just add those two guys together. So you got a grand total of 112 people. Okay. Okay.
Could you write it down on the steps to do this?
Sure. I can do that real quick.
Hey, please. I'm not smart guy.
I don't
Until
know
I
that
see.
I'd agree with you there. I think you are. I'm gonna write it down real quick. On each one, so the first one was how many preferred supreme pizza? That was 10%. So you multiply 10% by 320. Yeah, so the first one had us finding 10% of the 320. So you just do 0.10 times 320 and you get 32. The second one is asking for how many more people preferred pepperoni over cheese. So you find the difference in those percentages, which is 25%. And now we need 25% of that 320. So we're going to multiply those 0.25 times 320. We get 80. Then the last one was how many people did not prefer pepperoni or sausage. So that was looking at all the other sections other than pepperoni and sausage. So that was 10% for supreme. And then 25% for the cheese. So that gives us a total of 35%. So we need 35% of that 320. So you do 0.35 times 320. And we end up with 112.
Oh, okay. Yeah, because the last time on the little test, I just didn't have an idea what to do with this with this stuff. That's why I asked you to write it down.
Just a little
Steps.
trickier to keep in your head. Yeah,
Yeah.
that's fair.
Yeah, that's why. Now I will check this as many times I can.
Yeah, of
Thank you, man.
course. Yeah. Right, that's really all I have for you guys with charts and graphs. The next stuff we're going into is lines. We have lines in the coordinate plane.
Okay.
So all linear equations can be shown as a graph of a line. Makes sense? Represented on what's called a Cartesian plane. So you have that flat plane, and then you have the axes. So across the horizontal, so left and right, that's the x-axis. And then for the vertical, so that's the x-axis right here, is the horizontal, and then the vertical is the y-axis. So the center point is designated to kind of be called the origin point because it's, you know, dead center. So that's the point 0, 0. So if you look at the way a point is set up, it's always in parentheses. Then you have the x value, comma, the y value. Let's take a look at one of those. So in this case, the point given is 3, 4. So the x-axis coordinate is first, and then the y-axis coordinate. So in order to be able to graph this, what you do is you start at the origin, and then you say, okay, what do I have 3, 4? 3 is on the x, so you move 3 in the direction of x, 1, 2, 3. And then 4 in the direction of y, so you move 4 and y, 1, 2, 3, 4. Put a dot, and then usually you want to show what that point is, so I usually will write that next to it. You'll do that not all the time, but at least at the beginning when you're doing these plotting points to find lines. I recommend diagramming what your points are. So here's an example of a line on the coordinate plane. So that is actually the equation for 3x plus 2y is equal to 4, which is in the standard form of a line. Standard form is something x and something y is equal to something. For the most part, I don't like to use standard form with lines because it doesn't really tell us a whole lot. When we're working with standard form, you're not actually going to consider it working with standard form. So it's not really the most useful thing to work with. So what this is telling us is since we have 3x plus 2y is equal to 4, every point along that line is at a different x and y, and those x's and y's will make that equation true. So 3 of whatever the x value is plus 2 of whatever the y value is equals 4 for every point along that line. And that's how you graph them, is you end up finding multiple points that satisfy a given equation, and then you can just draw a line between them. Because if those ones are accurate, then every point in between is going to end up being accurate. Okay. So the first thing you do, way you graph these is graphing by plotting points. And usually you'll be given a little XY table off to the side. A lot of times you're given the X values. A lot of times you're not. When you're just learning, it usually gives you the X values, but eventually you kind of have to pick some out for yourself. Which sounds like it could be complicated until you realize that a line extends in every direction forever. So no matter what X value or Y value you plug in, there is going to be a corresponding value for the other side. So Our standard example here is going to be 2x plus 1. So y equals 2x plus 1. You can find sets of numbers or sets of points along that line by substituting a number into one variable and solving for the other. In this case, we're going to be plugging things in for x. That'll output something in y, and we'll just use that to fill in our table. So you have to keep the numbers small in order to have your graph closer to the origin. That way you don't have to use up a ton of paper, right? That's really the best advice I can give you for being able to plot certain points is just keep them simple, keep them small, keep them basic, and don't, no reason to overcomplicate it. Okay. Now on the left, we have an example of how you would plug in a value, and on the right, we have that chart filled out. So on the left, we were given the x values, we just didn't know the y values. So if y is equal to 2x plus 1, then it would make sense that if you plug that x value in, it'll spit out the right y value. That's what we do. So the first one is when x is -2. So you plug it into the formula, y is equal to 2 times -2 now, plus 1, which is -4 plus 1, which is -3. And then you put it in your chart. And you would do that 3 different times. You plug in a 0 for x, 2 times nothing plus 1 just cleans up to be a 1. And then you plug in a 2 for x, 2 times 2 is 4, plus 1 is 5. So you work all of that out, you get your tables, and then what you're going to do is you're going to take each of those x, y's and graph them on the plane the same way that we looked at that first problem, or that first point. So we have -2, -3. So you would start at the origin, go -2 in the x direction, -3 in the y direction. Draw your dot and label it -2, -3. Next point is 0, 1. So 0 in the x direction, 1 in the y direction. So you'd be right here. So you'd be at the point 0, 1. And then 2, 5. So 2 in the x, 5 in the y. Draw your dot, fill it in there. Now at this point, you would look at your 3 points and ask yourself, are they along the same line? Now, hopefully they are. If they're not along the same line, then you made a mistake somewhere. See, because technically, you can actually plug in 2 points. And if you do 2 points, you will always get a line between those 2 points. But that third point is kind of a check. Because if you make a mistake on 2 points, you're not going to know it. But if you do 3 points, well, you do 3 points, if you make a mistake, they're not all going to fall on the same line. So generally, if you do this and you have 1 point kind of out here and these 2 lining up nicely, then you know you made a mistake somewhere. So you go back and check your answers, make sure everything's okay. Now, if they are along the same line, then you could be reasonably sure you have the right answer. And you just take those 3 points and you draw a line between them. Now that covers all the little fractional points along that line that we wouldn't normally graph. But see, since it covers everything, goes on forever in this direction goes on forever in that direction. This will cover every single answer to the equation y equals 2x plus 1. Okay. That's pretty much it for that concept. Do have a couple of examples for it. I'm going to be a little picky with these. I'll probably only do number 1 and number 4 in the interest of time. You might say, why am I not doing number 2 and number 3? Because those are in standard form and they're more annoying to plug in for. Yeah. So we do, of course, need to have some points for all of these. So my X values I'm going to plug in. My personal go-tos are -1, 0, and 1. Because those are all around the origin. One is to the left of the origin, one is to the right of the origin, and one is on the axis. And that usually gives me a pretty good idea of what my graph is looking like. So that's why I usually will pick, these numbers here. So what you do is you're going to take each of these X values and plug them into this equation. So y equals 3 times X, and in this case, X is -1 minus 2. That's -3 minus 2, which is a -5. Now we plug in the 0. Y equals 3 times 0 minus 2. Well, 3 times nothing is nothing, so -2, just -2. Then plugging in the 1 for X, Y is equal to 3 times 1 minus 2. So that's 3 minus 2, 1. Now, when it comes to drawing your graph, some people do it one way, some people do it another way. I'll show you the way I do it. The way I do it's kind of lazy, I'm not going to lie. But what I end up doing is I end up looking at the ranges of numbers I have over here. So my X values only go from -1 to 1. My Y values are as low as -5 and as high as 1. So when it comes time for me to graph this, I'm not going to need a whole lot of room left to right. And I'm mainly just going to be dealing with the negative on the Y. So we'll kind of do it that way. I don't know why I made it go further in the right, but whatever. And you want your points to be kind of the same distance apart. That way the graph is the most accurate. So we start at the origin, and we're going to graph all 3 of these points. I just got a text message for Elizabeth for you guys. She's asking me to share with you guys that she's gonna be in contact with you guys no later than next week to discuss each of your individual plans.
Okay.
So that is the message. The message has been relayed,
Okay.
and I'm gonna go ahead and respond to her.
Okay.
So we got to graph these points. So our first point has the x value -1 and the y value -5. So we're going to start at our origin. And we're going to go -1 on the x and -5 on the y. 1, 2, 3, 4, 5. Right there. And I'm going to go ahead and label that -1, -5. Now, another reason that we label our points at this point is to make sure that if we go back, if we make a mistake and our 3 points are not going to be on the same line, we're able to look at our label and say, oh, is that correct? Which in this case it is. Then our next point is going to be given as the x value being 0 and the y value being -2. So the x value is 0, so when you start at the origin, we're not going left or right at all. But we are going down 2 in the y direction. So we're going to be right here. And another label, 0, -2. And our third point, love it, 1, 1. So you start at the origin, 1 in the x, 1 in the y. There we go. And we look at this and say, hey, are those all along the same line? Well, yeah. You know, other than my line being slightly crooked, but, you know, perfectly fine. So we'll go ahead and draw a line between them. And there we are. Not too bad, yeah. All right. So our next one is y equals 2x minus 4. Same general idea. And I'm going to go ahead and use the same points. Just makes life easier. So again, we're going to take these x values and plug them in for our y. We have y is equal to 2 times, instead of x, we have -1 minus 4. So -2 minus 4, we get a -6. Then we plug in a 0. That part's just gone. We end up with a -4. And we plug in the 1. So I get 2 minus 4 is a -2. You actually see kind of a pattern happening. On the last one, these points were all 3 apart on our y. And this one, these are all 2 apart. There's a reason for that, kind of ties into the next stuff called the slope. We're going to go ahead and graph these. I need about the same distance as last time. So for our first point, we have -1, -6. So -1 on the x and -6 on the y. Next point is 0, -4. So again, no direction on the x, -4 on the y. It'll be down here. And then we have 1, -2. So 1 on the x, and -2 on the y. These 3 points are along the same line. So we're good to draw a line between them. You always put the little arrows on the ends of that line because that shows that those are going on forever in both directions. Yeah. So we got our 2 graphs. That's all we got for that. Now, like I said, you can kind of see how those points are relating to each other. They were kind of moving up and over roughly the same distance each time. And that's for a reason, because they have the same slope between those points. So moving forward from that type of graphing, we need to understand what the slope is. So that's kind of the way that the line is angling, is its slope, right? And it's found using 2 points from a line and plugging them into this equation. The idea is that you're finding the difference in the height between 2 points and the difference between the width of those 2 points. And you're kind of making a ratio of it. When you make that ratio is going to be true of any 2 points on the entire graph anywhere, even if you plug in like 5 billion for x. Now, this is where it makes a little bit more sense. So the points you're using, those little subscript numbers are just designating different points. So y2 and x2 are part of the same point. Y1 and x1 are part of the same point. So when it comes to conceptualizing the slope, since it's difference in height over a difference in width, you like to think of it as rise over run. That's a very, very useful way to keep it in mind. Rise over run, because the change in y is the rise, and the change in x between the 2 points is the run between those points. So the next slide is just an example of one of these slopes being found. So this is all the steps. So going back to the example of y equals 2x plus 1, going with a couple of the points. Some of the points are -2, -3, and 2, 5. Okay, so we got these points here. Now, it doesn't matter what points you pick on the line, or in what order they are, as long as they're on the line. It doesn't matter which ones you work as 0.1, which one is 0.2, does not matter. You will always get the right answer for the slope as long as you keep it straight. And what I mean by keeping it straight is noticing that y2 is over x2 and y1 is over x1. If I lead with one point here, I have to lead with that same point down here. As long as you keep it straight, you are good. So if you're considering those 0.1 and 0.2, the idea with these points is that -2, -3 would be x1, y1, and then 2, 5 would be x2, y2. So for this part of the formula here, all you're doing is this y minus this y on top. And on the bottom, it's this x minus this x. So this minus that on top, this minus that on the bottom. And since both of those are subtracting negatives, you change them to pluses. And you just clean them up and reduce if you can. In this case, you absolutely can. And the slope ends up being just a 2. M is always designating our slope. Okay. Now we actually use this concept, the slope, in our other form of the line. We covered standard notation, which is, or the standard form, which is ax plus by is equal to c. For the next idea, we use the slope intercept form of a line. Now, personally, 90% of the time when I'm graphing lines, this is what I'm going to be using. It's far easier to work with. And you can actually, after this little section, we actually have a way of graphing where we just eyeball this. So it's called the slope intercept form because M is the slope and B is the y-intercept. So the y-intercept given as a point is, 0, comma b, because it sits on the y-axis. So it doesn't move in either direction on the x. Okay. So the next chunk of them, and again, I'm only going to do certain ones of these. Just for the sake of speed and covering our bases here. I'm going to do number 1. I'm going to do number 3. Going to do numbers 7, 8, and 9. So there's not a whole lot to this. That's why I'm only doing a few. These ones are incredibly easy. These ones we actually have to work a little bit. So again, we need our formula. So it's y2 minus y1 over x2 minus x1. What you do is you pick one of your points to be 0.1, one of your points to be 0.2. So let's say this is x1, y1, which would leave this to be x2, y2. Now from here, all you got to do is plug things into this formula. So we're going to have y2 minus y1, so 5 minus 2, over x2 minus x1, 2 minus, and be careful because we're subtracting a negative, -3. And what that's going to do is it's going to flip that sign to a 2 plus 3. Now we end up with 5 minus 2 on top, which is 3, over 2 plus 3 on bottom, which is 5. 3 over 5, we can't reduce that, so that is our slope. Now, same idea with number 3. We just pick one point to be x1, y1, one point to be x2, y2. And we're going to do the same thing. So it'll be y2 minus y1, so -1 minus 3 over x2 minus x1, so 6 minus 7. End up with a -4 on top and a -1 on the bottom. And all we got to do is clean those up. A negative divided by a negative is a positive. So this just ends up being a 4. That's it. I'm going to turn off the projector because nobody else is here. And all I hear is it's kind of quiet fan hum.
Nobody there?
Nope. Just you two online.
Oops.
Yeah, that's fine. It's the last class. I always only have a couple of people left.
Typical all the time, huh?
Oh yeah, most people don't show up to the last one. I'm not gonna lie. I think last time I taught this, wasn't it just you on the last day?
Yes. Yeah.
Yep. See, there we go. This time I at least have 2, so I'm cool with it.
Yeah.
All right. So now we have 7, 8, and 9. And like I said, these ones are quick because we have the formula. These are all in the form y equals mx plus b, where m is our slope. So for all of these problems, as long as they're set y equals, whatever is attached to the x is our slope. So for number 7, the thing on the x is 3. So that's our slope. That's it. For number 8, thing on the x is 2. So that's it. And for number 9, thing on the x is -1/2. So that's our slope. So being able to identify the slope can be pretty easy when it comes to the formulas. But see, identifying is one thing, you need to be able to work with it, right? That's the main bit. Okay. So being able to use the slope intercept form is incredibly useful. So slope intercept form, the y equals mx plus b, is arguably the most useful form as it allows us to get all of the necessary information to graph it at a glance. So the easiest way to consider the slope is to consider it as m equals rise over run. Because if you have it as a fraction, the top is how much each point is going to rise from the previous point, and the bottom is how much each point is going to run from the previous point. So if you know the rise over run from any point, you can find another point on your graph. So the b point value, the y equals mx plus b, the b value, you kind of use that as a starting point. So that's always going to be your y-intercept. So it gives you one point on the graph where it's crossing the axis. And then from there, you do rise over run and get your next points. Okay. Now, sometimes they're not in slope intercept form. Sometimes they're not in slope intercept form. So how do we get them into that form? So converting back and forth is actually pretty easy. So to convert an equation into slope intercept form, you have to solve the equation for y equals. You just kind of get it into that form. So for instance, here, you have 4x plus 6y is equal to 8. The idea is that you're going to want to solve for y. If we're solving for y, then you're going to get rid of the 4x term. So you subtract the 4x from both sides. And since on the original formula, y equals mx plus b, the term with the x comes first. That's why on the next line, we have 6y is equal to negative 4x plus 8. Put that x term first, so it fits that formula. So you have 6y is equal to negative 4x plus 8 at this point. And then in order to solve for y, you have to divide everything by 6. So negative 4x divided by 6, 8 divided by 6, divide everything by 6, and reduce if you can. So you end up with negative 4/6 x. That reduces to negative 2/3 x. And then 8/6 on the end reduces to 4/3. So that one would be kind of rough to graph because it has fractions in it, but it is still doable. It's awkward, but it's doable. That's generally how you work with those. So what we're going to do, we're going to graph a few of these. Let's see, I'm going to do number 1. I'm going to do number 2. Then I'm going to do number 4. And then we'll see if we need to do more from that. So each of these we're going to be graphing. And we're just going to graph these with slope and intercept. It's monumentally faster than using points. So this one isn't set into our formula, so we need to get it that way. So we're going to solve this guy for y equals. It's not far off. We just have to subtract the 2x on both sides. So on the left, we have a y equals left. On the right, we have 2x, 2 minus 2x. So you want to have that minus 2x part first. So minus 2x plus 2. And from here, this is where we're going to graph from. So what we're going to do, we're going to look at this and understand a little bit about how it's written. So we know our slope is -2. So what you want to do is kind of think of that as a fraction and put it over a 1, and think of that as rise over run, because that's going to make our life a lot easier when it comes to graphing. Now, graphing this guy, not too bad. This is going to be one of the worst graphs you ever see from me. Graphing this guy, what we do is we find our y-intercept, which is this +2 right here. And we go up to that 2, and that's going to be our first point on the graph. Now from here, we use our slope to find the next point in the graph. We have -2 rise, 1 run. That means we're going to go down 2, run 1. There we go. There's our next point. Every one of the points is this far apart from each other. So down 2 over 1, down 2 over 1. You can even go the other way around, where you would go back 1 and or up 2 and back 1, and that would work. But see, as long as I'm starting from my y-intercept and I'm using the rise over run from our slope, look how many points I just did, 5 points. That would have taken us a little while if we were doing the charts, right? Now, the tricky part is if you're incorrect about this, how you draw your own line is probably going to be the same, whether you're right or wrong. So you got to be careful about how you work these out. Now, one way that's particularly useful to be able to wrap your head around is if you look at this, your slope is negative. If you have a negative slope, that means this thing is facing downwards. It is pointing down. Now, this one over here on number 2, this one has a positive slope. So this one's actually going to be aiming upwards. And the same thing with number 4 here has a negative slope. So it's also going to be going downwards. So being able to understand kind of the slope helps out a lot. So let's look at this one and see about graphing that. Now, again, I'm going to look at my slope to 3. I'm going to put it over a 1. I'm just gonna write rise over run next to it. Just kind of keep that, helps me keep it straight. Okay. So. Draw our graph. If I need more points, I'll draw more points. I'm not too worried about it. So our y-intercept is -2. So we're going to start at -2 on our y-axis. And then our slope is 3 over 1. So we're going to rise 3, 1, 2, 3, run 1. Okay, and we're going to do it again. Rise 3, run 1. I got 3 points now. Should be enough to draw a line between. And there we are. So these aren't too bad, right? You just start from the y-intercept and then move up and down depending on your slope. So we're going to go ahead and graph this one next. Now, when I have a slope that's fractional, what I like to do is I like to put that negative on top. That way I can kind of concrete think of that sign going with either my rise or my run. That way I can keep it kind of a little bit more straight. Because if I just had that negative out here, I wouldn't necessarily know where my negative was for my rise or my run, right? Okay. We're going to go ahead and graph this guy. So again, I'm going to start from where my y-intercept is, which is 2. Now my rise is going to be a -1, so I'm going to go down 1, and then my run is 2. I'm going to go down 1 over 2. Down 1 over 2. Down 1 over 2. Like I said, I could also go up 1 and back 2. There we go. I can do that as many times as I need to. See, we just got 7 points. That's a lot of points. Draw a line between them. And we are good to go. Not too bad, yeah?
Yeah, much easier than the other ones.
A little quicker. Don't think I have enough time to actually cover my last concept. So unfortunately, I think the class is over.
Okay.
I know you're gonna miss me, calm down.
I will see you on July.
Yeah, I think it's what, the 11th is when the next class starts?
I don't know the date yet.
Yeah, it's July 11th, so about a third of the way through. And it lasts for a little bit. I know that the summer class is gonna be a little bit different. Gonna be more hours, but shorter classes, because it's gonna be Tuesday, Wednesday, and Thursday, and instead of 6 to 8:30, it's gonna be 6 to 8 each day. So we're gonna have a little bit more time to cover stuff. I'm gonna start at the same point and work until we can't work any further.
Exactly.
Yeah.
Okay. So all the videos is gonna be in YouTube.
Yep, I'm going to, obviously, I'm still kind of feeling sick. So I'm going to not do that tonight, but I'm gonna try to get that done this weekend. On the off chance that I completely forget or something, just shoot me an email, remind me. Just get on me about that if you need resources.
It's
I will get you your resources, okay?
okay. So we have in total 13 classes on math this session.
Yep, it's that way.
Okay, because we have time all this month and something to go back and checking again and again.
Yeah,
Yeah. Okay, thank you, teacher. I really appreciate for you patient.
always happy to help you. Look
Mhm.
forward to seeing you again.
Okay, see you again.
Have a good night, everybody.
Okay, you
Okay,
too.
thank you.
Thank you,
Bye.
thank you.
Bye.